Well, let's get started. We are going to finish off this section on chapter 3 and hopefully get started on the next one. Scatter plots and regression. We're going to look at a thing called the deterministic formula. Now, normal scatter plot formula, you have the data and it's got a little bit of randomness to it, hopefully not too much. And there's this special line, right, correlation equation that goes through the data, and it's basically the best fitting straight line that you can. But sometimes the information that you get is a perfect straight line. Now, that can happen in a story where there is a distinct formula that tells you how to do things. So in this story here, when you get a perfect straight line, right, there is no variation. It's called a deterministic formula. So it's not a correlation formula, it's a deterministic formula. And so what you have here is a story about a salad bar that charges you by how much in weight your salad costs. And the formula is -550 plus 0.55 times the weight of the salad. So they take the weight, and if you get, oh, by the way, the weight is in ounces. So you go to the salad bar and let's suppose that you fill it up with 5 ounces. Then the price that you will pay is -550 plus, check this formula because I may have written it wrong now that I'm looking at it. I think that might be 5. No? Is that 5 ounces? Okay. I want to make the question realistic. 15 ounces. Then you get charged this guy times 15 ounces. And it's just like the other kind of questions. So we go -550 plus 0.55 times 15. And the answer is that salad would cost you $2.75. And the reason why that is 15 is I forgot to mention in the story that the container weighs 10 ounces, so that when it's 15 ounces, it's really 5 ounces a salad, right, and 10 ounces a bowl. So they're not going to take your salad and dump it out in a scale and weigh it. So what they do is they weigh the whole thing, but they know the bowl weighs 10 ounces. So if your bowl weighs 15 ounces, you're really getting 5 ounces of salad. So that's how it works. This is a deterministic formula, right? Because it's an exact formula based on how many ounces, essentially, your bowl plus your salad would weigh. Another example of that, very simple one, because I can't think of a hard one. Imagine this deterministic formula, and it was being used for gasoline, and it's $3.96 a gallon, and X is how many gallon, and Y is the cost. And they tend to use Y's and X's when it's a deterministic formula. And me personally, I like to return to a formula that kind of helps me understand what's going on. Can you see in this formula here, if you go to a garage, right, and you do 2 gallons or 2.1 gallons or 87 gallons because you've got a huge truck or whatever it is, isn't the amount that you pay a fixed amount, and won't this formula do it? It's a formula that doesn't have any variation. If you went and collected 20 cars and put on the x-axis how many gallon they got and put on the y-axis how much they paid, wouldn't it be a perfect straight line? Right? So deterministic is just a special example of a scatter plot where the data is on a single straight line, and therefore the equation you get is the exact value that you would pay for salad or for gasoline or for whatever the story is. So you will see some situations where that is happening. Are we okay with this new guy called deterministic formula? You still have a formula, you still plug in numbers, and you still have the same kind of questions that can be asked, like, isn't the slope in this question here, isn't the slope how much more you will pay if you increase the number of gallons by 1? So if you use 1 more gallon, you'll pay $3.96. What would the 0.55 here in the salad story represent? 1 more ounce of salad, you will pay what? So for every extra ounce of salad, you will pay what?
55 cents.
55 cents. Does that kind of make sense? Now, we talked about this last time. The y-intercept doesn't always make sense. Agreed? Sometimes the y-intercept just doesn't make sense. Would you agree in the context of this, the y-intercept doesn't make sense? Right? It has no valid meaning. Now, in this case here, won't the slope be for every extra gallon you pay another $3.96? And technically speaking, isn't the slope plus 0? Right. In this case, it kind of does make sense. Isn't the y-intercept of 0 means if you don't buy any gasoline, it will cost you nothing? Right, so I guess in that case, it did have a sense. Any questions about that? Or we go? Yeah. There's a whole load of questions on calculating some deterministic ones, and then we just kind of jump around and we do some of the correlation ones. So here is a version of question 12, and I'm not going to change it this time. That's the formula. X is degrees in centigrade and Y is degrees in Fahrenheit. So if you wanted to find out how much 70 degrees Fahrenheit was, you would do that. Have I got the right way? My apologies. If you wanted to know what 70 degrees centigrade looked like, got them back to front, you would get, here we go, 32 plus 1.8 times 70, and it would not be a good place to be, because the answer would be 150 degrees Fahrenheit. I have never been in 150. I've been in 112, I think it was, in Vegas. Anybody been close to 150? Maybe you were in the desert. Just curious.
I went to Egypt. I don't know how hot it got, but I'm pretty sure it got pretty close.
So it could well be in that it was like burn your skin hot.
Yeah.
Gotcha. Okay. So if it's a deterministic formula, for all intents and purposes, don't you do the same kind of thing that you do with a regression equation? You just plug in an X and you get a Y, or you plug in an age and you get a height, or whatever it might be. Now, the next question, 13, is a data set. It gives us an equation based on the data. It's not a deterministic one. And when it's not deterministic, it means it's a regression equation. And it's this weird looking fella. And do you see a funny little, well, it's a caret symbol, but it's called a hat. So if you want to say that out loud, you say Y hat. When it's deterministic, they use Y. When it's regression, they use Y hat. I do not like that formula. If I go back to the storyline, I can tell you what they are. It's 113.584, take away 1.006, the latitude. And what else do we have here? And Y is the August temperature. So when you write the formula like that, it makes it a lot easier when they then go and ask you things like, suppose the latitude was 30 degrees. Then wouldn't the August temperature be this ugly decimal, take away 1.0006 times 30? And I'll just do that right now. So it's 113.584, take away 1.0006 times 30, and the answer is about 83.566 degrees. So if you stay in a place that has a latitude of 30 degrees, your average temperature in August would probably be about 83.5 degrees. Right, you remember doing some earlier questions with, I think it was January, because it was the same kind of day. While we're on this fella, there is a y-intercept, oops, and there's a slope. So let's do those questions because they very often ask those. In this question, the slope is negative 1.0006, really ugly number. What does that tell me? Well, for every extra 1 degree on the latitude, doesn't the August temperature decrease by, oh, can I just say 1 degree? Well, I guess I'm being fussy by that number, right? Isn't that what the slope means here? Right, so for every time you increase this guy by 1, the temperature goes down by that amount. And they also have a y-intercept. Okay, let's interpret the y-intercept. What does that tell us? Well, it tells us the August temperature. Where? What latitude? It's on the equator, yes. A latitude of 0 degrees, which is called the equator. You all know that, you know, the world like that. Well, that's 0, right? That's the equator, right? And then that's like, you know, 10 degrees, 20 degrees, 30 degrees from, and then you end up at the North Pole, don't you? I think the North Pole got a latitude of 90 degrees, I think. Goes from 0 up to 90. So, are we cool with the questions that are the usual ones, which are the regression equations? And you tend to get questions like, okay, use the equation to find the temperature at 30 degrees latitude. And then they might ask you, what does the slope tell us and what does the y-intercept tell us? That's the 3 main things that happen. And I'm going to show you this question. It's easier to show you than to read it out. So you bear with me for a few seconds while I load it up. Right. See if I can make it a bit bigger for some of your screens. There we go. Imagine a regression line that relates the average systolic blood pressure to your age. So you collected data on, say, 100 people at different ages, you know, 12-year-olds and 82-year-olds, and you took their average systolic pressure. So you went in and you maybe measured it in 3 or 4 different days just to get an average, right? And you plotted that number. You get a scatter plot, right? 12-year-olds would be down here somewhere and 30-year-olds would be over here. And in this story, they only tell us 2 of them. For a 30-year-old, it came out about 115. And for a 55-year-old, it came out as 125. Right? And only with that information, we are going to try and put together, or try and answer these questions and then put together an equation. So I'm just going to write these numbers down now. So a 30-year-old has a 115, and the other one was a 55-year-old, and they had a 125. And this is going to look like math. So you don't get a lot of math, but this is one of them. Now, I'm making no attempt to do this accurately, but can you imagine that was 30, and can we pretend that that's 115? Then if I move over to 55, won't 125 be maybe a little bit higher? We'll be here. Only because I have two dots, I'm going to have to make a big assumption. And that assumption is that the rest of the data follows that pattern. Can you now tell by looking at my very badly drawn scar plot of two dots that isn't the evidence that that's going to be a positive slope? And so the first question is, what slope is this regression line? And the answer is positive. Right. Now, I would like to know more than positive. This is where the math comes in. Can you remember doing this funny little thing in Math 99? Why do you think I'm adding these two little dotted lines here? I'm going to find the slope. Isn't the slope the rise over the run? You remember that from Math 94, 99, wherever you got it? Now, in this question then, the distance from here to here is called the rise. And would you agree from there to there, it's 10. So far, so good. Now, the fellow that goes from here to here is called the run. And from there to there, I believe, tell me if I'm wrong, I believe that's 25. So if I wanted to get the slope, yes, it is positive, but I would like to put a number on that positive. The number I'm going to put on is 10 divided by 25. It's going to have a slope of 0.4. Okay. So in the box in that question, when they said, what is the slope? I'm not going to write positive. I'm going to write positive 0.4, right? I'm going to actually write a decimal. That makes sense so far? Now, that's not normal things that we do in statistics, but occasionally we do maths. Now, the next one's going to be harder. I need to find the equation of that line. Now, I don't know who you get taught by, because I know there's at least two versions of this formula. I'll put down the one that I think you might have seen, because this is the most common one. Have you ever seen that equation for calculating a line? Y minus y1 equals m, x minus x1. Have you seen that guy? Some of you are nodding. Have some of you seen y minus b equals m brackets x minus a? That's another common version of that. Is that the one that you saw? I mean, it's the same equation, just different way of writing it. Okay. Which one do you want me to use to get the equation of the line? Because they're going to be top one, number one. Okay. So y
do we
minus
not
y.
have plus like plus b on there? Like y equals mx plus b? I don't quite remember.
Oh, that y equals mx plus b would only work if I know the y-intercept, but since I don't, I can't use that formula. But yeah, there is one that looks like that as well.
So it shows up usually when you can solve for it, right?
It shows up if you know the y-intercept, because that's what b would be. But in this case, I don't. Now, x1, y1, those two guys. Pick any one of those 2 points. I'm going to pick the first coordinate. And he is x1 and y1. And m is the letter for the slope. So it's going to be y take away 115 equals 0.4 x take away 30. Now that's the equation of the line, but I don't leave it like that. Can you understand that it would make sense if I make it a little bit prettier, right? A little bit easier to deal with. So first thing I'm going to do is just multiply, distribute the 0.4. Okay, what do you think I'm going to do next? And that's basically us finished. What am I going to do to this to make it look like that?
Add 115.
Yeah. So we now have, add 115, I believe that's 103. Here is our guy. In this case, this is your blood pressure is 0.4 times your age, add 103. And the reason I need that equation is because in question 15b, they say to us, estimate what a 45-year-old's blood pressure would look like. So if you go in here, an average kind of normal kind of person aged 45 would have a blood pressure of whatever that comes out to be. So 0.4 times 45, and then add 103. Any of you who are in the nursing program, does 121 seem like a reasonable kind of number for a systolic blood pressure? At least for a 45-year-old. What this particular formula now allows us to do, if it's accurate, and I'm assuming it is, couldn't you put your age into that and find out what a typical person of your age, what their blood pressure would be like? And then if you found out what your blood pressure was, couldn't you find out if it was higher than a person of your age or lower than a person of your age? And because it's not an absolute value. You know, an 18-year-old's going to have a different blood pressure than an 80-year-old, right? And doctors know this. I don't know if they use equations like this or whether they just know it in their head, right? You're 60 years old. You probably should have the number run about this. It's a little bit high. Maybe I need to give you some blood pressure medication. Or it's a little bit low. Maybe I need to give you whatever you give people when their blood pressure is low. And if it's bang on that value, then that particular thing is good to go. Okay, pause for a minute. Are we good on that question? Did you see that even with a very limited amount of information, can't you at least create an equation that you could use to predict other values that you didn't know beforehand? Would you also agree it's probably a good idea to collect lots and lots of data so that you get a more accurate straight line? Because the two that they gave me, they could have been atypical. Couldn't they be a little bit different than the typical person of those ages? In which case my equation would be flawed. I'm sure that the equations that they use in the medical world are really good, because aren't they probably based on hundreds of thousands of data that they've collected, you know, over time? Let's show you a visual one now. So I'll stop sharing that. And here is a homework question with a scatter plot in it. So the following is a scatter plot of pulse rate after marching in place for 1 minute versus the resting pulse rate measured before marching. I guess military do things like that to check the health of the recruits, right? You know, they check your pulse rate, and then they take you all out and, you know, get you cardio, and then you take your blood pressure, you take your heart rate, or what is it, your pulse rate, I should say, again. Would you agree that this is positive? What do you want to do? Strong, moderate, weak? Moderate? Okay, we know that's a bit arguable. What else do we need to say about this one? Linear? Do you think it's linear? As opposed to curved? Right, I think all those, the standard kind of questions that you're being asked. Now, do you see here they gave us the way I like the formula to be written, like with words, so it makes more sense. So in here, you plug what the resting one is, like 80 or 50. And then if you plug it into here, it will tell you what the marching pulse rate would be. So when it says what's the slope of this equation, isn't it just a matter of knowing where to look? Pretty standard question, right? And then it goes and says, well, what does that mean? And then it says, predict the pulse rate at 55. Can you imagine I just go to this equation and plug in 55 and get the answer? Do it at 75, well, you know, plug in 75, get the answer. Kind of standard questions, right? No frills, pretty much what you get asked a lot. And then it said, use these two results to pick which one of those four would be the best fitting straight line. Because you imagine if you've got an equation, which you have, if you wanted to draw a straight line using an equation, wouldn't it simply be a good idea just to plot 2 points on the line and then join them up? That makes sense? And so once you know the answer to this one, won't you know what 55 comma the second number is, and then 75 comma the number, and then you go 55 this guy, 75 that guy. It looks like it's this line rather than that one or that one or that one. I'm going to do a slightly different version of that story. I am going to say that one could never be the right answer, just by looking. Why do you think that line on the top picture is unlikely to be the best fitting straight line? Just visually, why is it bad?
It isn't in the middle of the data.
Yeah, would you agree there's more dots above it than below it? It's not in the middle. And do you know a best fitting straight line? Kind of intuitively, shouldn't it be in the middle? You know, for that reason, would you agree I could kick out that bottom one? So I haven't done the straight line thing that they're talking about yet. I've just looked at the choices and said, it's definitely not those two. Now, it's a little bit harder when I look at the two that's left. I agree? And I can't tell them. I think you'd need to figure out by finding the 2 points that they tell you and see which one of those two lines it's in. They are so close to each other, I wouldn't even want to guess. But one of those is the right answer.
We get 5 tries, right? No, just kidding.
Oh God,
Don't do
that's
that.
true. You get 5 tries, so you're going to figure it out eventually, right? Yeah, yeah. But you know, it would be good if you could do it the real way. Nothing happening there. That's pretty standard, and that's standard. So, as far as I'm concerned, we have finished that section. Are you comfortable that you could answer the kinds of things that we've done today, the deterministic equation and scatter plot of various types? Are we good? Right, I get nods. Nods is good. If you bear with me. Right. Okay, so what is our last section about? Well, it's really still regression. It's regression lines. Oh, I'll put it on. Going to talk about regression lines a little bit more. imagine that we had some data. I'm just going to call them X's and Y's, but it'll be things like age and blood pressure, whatever the story is. And you got your usual scar plot. It looks like this. And that's nice. And then you've got another different question. And you get a scar plot. Kind of looks like that. And then you've got a third one. And I'll go down the way for a change. And you get a scatter plot. And it looks like that. None of these are deterministic. We're not going to do anything else on deterministic now, right? That was just a little side issue. They're all clearly not perfect straight lines. And right now, the kind of terminology that we use, and I'm just repeating myself here, is if I draw my little sausage, would you agree it's positive? That it's linear? And I'm going to go for moderate. Now this bottom one, here's my sausage. I'm going to say this one is negative association. Again, it's linear. And I'm going to go for strong. I hope you agree with me. At least I tried to draw it so it was strong. And then we got that guy. I'm going to put another dot there. Positive, negative, or no association?
No.
Great. Now, when you say no association, don't the other two things not really mean anything? You can't be linear and no association. No association means there's nothing going on. And you can't be strong, weak, or moderate when there's nothing going on. So when you say no association, you're pretty much finished with your description. And so if somebody says, I've got a scar plot and it's got no association, well, you think of a kind of big blunderbuss of shell shock. It's just a big circle of nothingness, right? No pattern that's even vaguely detectable. So what's the new guy in town? Well, we are going to now introduce a number that gets calculated by the software, so we don't need to do it by hand. And this number is called the correlation coefficient. And the correlation coefficient uses the little letter R. And the correlation coefficient is a number between -1 and 1. Okay. When the correlation coefficient is 1, your data is essentially deterministic. I would just say it's a perfect straight line. Yeah, you can't get any better than that, right? Every single one of your data points are all on the same single straight line. Have you noticed that the guys that we were doing here isn't the best fitting straight line? It doesn't go through all the points, agree? It's a wobble line, but you know what I'm trying to say, right?
Correlation also works like that for curves, right?
Ah, well, no, and yes. That's a bad answer, but I'll try and explain it later. R equals 0, and then -1. So let's go in -1. -1 is also a perfect straight line. Do you see that it's just pointing downwards, right? So if I tell you the correlation coefficient is 0.8, don't you know that it's a positive association because of that? And if I tell you it's -0.7, you know it's a negative correlation. That works really well with the plus slope and the negative slope as well, doesn't it? So all the terms kind of follow each other, right? They all kind of go together. Hopefully it's kind of obvious what a zero is. What would a correlation of zero look like if I did a scatter plot? Like that guy, yeah. So we can tell if R is greater than zero. So if R is a positive number, then you will have positive association. If R is a negative number, then you will get a negative association. And if R equals zero, you get no association. Now, these are all agreed in every textbook you're going to get, right? Because they're truisms, right? And R equals 1 is a perfect straight line. And if it's a positive thing, it's a positive association. Now, what I'm about to tell you now is not written in stone. If you go online and you try and look for it, there are going to be disagreements about what that means. But I'm going to give you my kind of rule of thumb, and it's only mine. Wouldn't it be nice if we had some way of at least deciding moderate, strong, weak? Agreed? If there was an R value or a range of R values that we would be able to say, okay, if it's this number, it's that. So here is mine and just mine. I've qualified it twice now. A strong association is an R value, right, that's between 0.8 to 1. Now, can I also, because I don't want to make this table big, won't a negative 0.8 to a negative 0.1 also be a strong association? Okay, so it counts in both ways. Right. A moderate association is going to finish at 0.8, and let's just hope there's no 0.8s in it, right? And you're going to be able to get to about 0.5. So 0.5 to 0.8 is going to be considered moderate association, right? And then weak is basically from 0 to 0.5. Now, technically, 0 is no association, but you're probably not going to get zeros. Can you imagine? Well, maybe you can, but can I tell you that no matter how random you make this circle of blobbiness, you always, just because of the way it's calculated, you always end up with some kind of number. It's like 0.02 or negative 0.1, right? It's so close to 0. So no association and weak association kind of blend in each other a little bit because of that. I mean, if there is a very, very weak association, isn't it just like saying there's none at all? I mean, there's a grey area in there, but it's hard to judge where it happens. So in real life, you'd never get a 0. If you just randomly pick 50 points, right, and just randomly put them out there, and you plug it into a piece of software, the R value will come out as nothing 0.1 or something like that, right? It won't be 0. I guess you could get 0. Make a square, right? That'd probably get you 0, right? But the chances of that happening are slim, right? Are we good? So we've got a new guy in town called the correlation coefficient that you get from the software, right? It's a really, really ugly formula if you ever go looking for it to see how you could do it by hand. Not that anybody ever would do it by hand, but you can have a look at it. Now, this is a side issue, but since Ashton mentioned it, I want to go over it. Let's imagine that I have some data that is a perfect curve. Like, can you imagine a data? I know that's not great, but can you imagine that's a perfect curve, right? Its R value is not -1. You agree it's decreasing, right? So it's a negative association, right? It's not -1 because this R value that we got, this correlation is how close does your data match a straight line? Would you agree that this data doesn't match a straight line very well? So if you did a correlation data on a curved set of data, you will find that it will be negative because it is going downhill, but it might be only -0.7. Because
What I had meant is if your fit line was also curved, we do that a lot in like chemistry and stuff.
You're beating me. Yes, you're right on ball. We are dealing with only linear correlation. That means straight lines. But there are other kinds of correlation. There is logarithmic regression, logarithmic correlation. There is exponential correlation. There is quadratic correlation. There's lots of different ones. So if you know your data was a quadratic or an exponential curve, you would do a different kind of analysis on it. You would do exponential regression on it, right? And in that case, the R value would come out plus or -1, depending on which way it was going uphill or downhill kind of thing, right? But for the sake of this course, we'll pretend that that's not an issue that we need to deal with, right? So we're only going to deal with how good is this data to being a straight line. Okay. And correlation coefficient does that. And now some more notes. This is called the coefficient of determination. And I don't know if this particular textbook uses that term, but it is quite a common one. And the coefficient of determination is called R². And it's almost always given as a percentage. Well, suppose I had some data and the correlation coefficient was 0.7. If I wanted to find the coefficient of determination, a lot of textbooks convert it into a percentage. Some leave it alone as a decimal. I guess we'll find out when you do your first answer. Now you might say, what's this 49% telling us? It's actually telling us something very interesting. It's phrased like this: 49% of the data, of the variation, apologies, in the data is accounted for by the model. That's like the lawyer sentence that you use. Right, so let's put that into words. Suppose we had some data and we collected that data and it was age and blood pressure, right? And we got our data that looked like that. And let's just say that the R value was 0.9, just for argument's sake. Then would you agree that R² would be 81%? Now, what does that tell us? Well, this sentence would be 81% of the variation in the data is accounted for by the straight line model. In English, that becomes 81% of the reason your blood pressure is the blood pressure that it is your age. In other words, the major factor in you having your blood pressure, right? 80% of it is based on your age. So if you ever hear questions where, or information that says your life expectancy, 50% of it is genetic, 20% is lifestyle, and 5% is something else. What they're telling you is the R-squared based on models that use those three things, right? For instance, if I was doing the blood pressure one here, 81% of the reason your blood pressure is that, doesn't that mean there's another 19% unaccounted for? Couldn't that be how heavy you are, right? Your weight. Couldn't it also have factors like genetics, like is there a blood pressure problem in your family, right? Is there an illness where a lot of you have high blood pressure? So it's not a perfect fit unless the data was a perfect straight line, in which case it'd be 100%. That is the only reason your blood pressure is what it is, and that's your age. Now, if R-squared is tiny, like 10%, well, doesn't that mean there's another 90% that you don't know, which is causing your blood pressure? And in that case, wouldn't that be probably a very bad model to use to predict people's blood pressure if the R-squared was only 10%? Right. So it's a useful number to know because it kind of gives you a kind of confidence on how much you want to believe the answer, right? If I had an R-squared of 92% and I was using it to predict something, would you agree I'd probably be pretty comfortable about using its predicting qualities? If it said this age should have that blood pressure, I'd be saying, yeah, it's probably going to be that. If it was a 10%, wouldn't I be saying, I might as well just guess, right? A 10% fit is nothing, right? There's tons of other things that are going to affect it. The answer could be miles away from it.